Okay, so we are finally in the very end stages, the electron transport chain. Electron transport chain. And if we just look at this for a minute and tally up what we have so far, for glycolysis, we end up netting a result of 2 NADHs and 2 ATPs. For the transition stage, we have a net result of 2 NADHs. And from the Krebs cycle, we have a net result of 6 NADHs, 2 FADHs, or 2 FADH2s, and 2 ATP. Now, mind you, this is including, remember in glycolysis, we divided this original glucose molecule in half. So everything from then on, after we divided it in half, we have to tally up a count times 2, because this is happening to 2 separate small halvesies molecules. So these tallies that I'm doing are the final tallies for both molecules that glucose is divided into. Totaling this, we have a total of, so far, we only made 4 ATPs total, but that's okay because the electron transport chain is where we're going to make just a buttload of ATPs. So that's fine. And then if we total up all of this over here, we have 2 NADHs plus 2 NADHs plus 6 NADHs. So that's 10 NADHs. And then we have a total of 2 FADHs, or 2 FADH2s. So our total that we have made of all these energy carriers so far, before we get into the electron transport chain, is 10 NADHs, 2 FADH2s, and we also made 4 extra ATP. Now, all of these, when we make them in whatever stage we're making them in, all of these, they are the NADHs and the FADH2s, these are going to go over to the electron transport chain and take part in this. So from the Krebs, we're going to have 6 NADHs and 2 FADH2s, but we also have 2 NADHs from transition and 2 NADHs from glycolysis. So that's going to give us a total of 10 NADHs and 2 FADH2s that all, after they're given off in their respective cycles, they all go over to the electron transport chain to be processed and turned into more ATP. Now, the electron transport chain is also called the oxidative phosphorylation cycle, because at the very end, there's like this pump with a rotor on it. It looks almost like a doorknob with a pump attached to it. So every time that doorknob twists, it pumps out ATP, and that's at the very end of the electron transport chain, and that is what is particularly called oxidative phosphorylation. But a lot of people just use oxidative phosphorylation as a general term for the entire electron transport chain. Now, we know that in glycolysis, brought the glucose molecule into the cell and divided it in half. The transition stage brought it into the mitochondria. The Krebs took place inside the mitochondria, and now the electron transport chain is in the cristae of the mitochondria and the intramembrane space, and inside the mitochondria as well. But the important elements that operate the electron transport chain are embedded in the cristae of the mitochondria, which are these folds right here, right next to the membrane, the mitochondrial membrane. So you see how this, right next to the membrane that is kind of like the cell wall, but for the mitochondria, right inside of there are these folded loop-de-loops that is another part of the membrane. It's a second membrane, and it's called the cristae, or some people pronounce it Krista. It's Krista. I think it's when it's plural, and Christae when it's singular, but I'm not sure. But some people say Krista, some people say Christae. So don't get confused that we're talking about the same thing. These folds, these up and down, this membrane that goes in these up and down folds right inside the actual membrane wall of the mitochondria. And in between the outer wall of the mitochondria, that cell membrane of the mitochondria, and that cristae, we have this gap, this margin between the cristae folds and that outermost membrane of the mitochondria. And this is called the intermembrane space, which makes sense, right? Because it's between the two membranes. And so if you have, like if you're in St. Louis like me, we have Interstate 70, which goes between two different states, between Missouri and Illinois, or whatever interstate you have wherever you're at listening to this. The interstate means it goes between two states. And so this would be the intermembrane space, because it's between it goes back and forth between two membranes, the crista and the actual cell membrane of the mitochondrial membrane, not the cell membrane. And of course, the mitochondria is inside the cell, so the cell membrane would be out here somewhere. So the mitochondrial membrane and the cristae, between them is the intramembrane space. That's also going to be abbreviated IMS, just so you know. So if I write down IMS, that's what I'm talking about. Now, at the end of the electron transport chain, we are going to see how many ATPs total these make, because the ATPs that we've already made, the 4 ATPs, they just stay ATPs. Nothing happens to those anymore. Once you hit ATP, you're done. But we have these 10 NADHs and 2 FADH2s. Well, this electron transport chain is going to show you why for every one NADH we have going in, we're going to get 3 ATPs coming out. And for every one FADH2 going in, we're going to get 2 ATPs coming out. So if we have a total of 10 NADHs from the previous 3 cycles, and every one NADH gives us 3 ATPs, that's going to give us 30 ATPs. And if we have 2 FADH2s from the previous cycles, from the Krebs particularly, and for every one FADH2 that's going to give us 2 ATPs, then 2 FADH2s is going to give us a total of 4 ATPs. So if you tally all of these together, the 30 and the 4, and then the 4 ATPs we already made, that's going to give us a total from the entire cellular respiration metabolism process, a total of 38 ATPs altogether. And the electron transport chain is going to show you these final steps where it turns the NADHs and the FADH2s into ATP. Okay, so the thing you need to know, just as a quick catch up before we go into the electron transport chain, is that you need to remember that NADH is, if you break down the components in NADH, we have NAD plus, a positive, NAD positive, and we have a proton, which is a positive hydrogen ion, which just means the hydrogen lost its electron, so it has no electrons, it just has the one proton. So that's why we call positive hydrogen ion and a proton the same thing. I'll do this. Same thing, okay? And we have 2 negative electrons, or electrons are always negative, but we have 2 electrons. So NADH, the components, if you break down NADH into its components, it's NAD positive plus a proton plus 2 electrons. Okay, now FADH2 is going to be FAD plus 2 protons plus 2 electrons. And I put down here just as a reminder because an H, if you go all the way down to the bottom of this page, just a regular old hydrogen, H, is a positive hydrogen plus its electron. Because if you have that hydrogen and you take away an electron, it turns into a positive ion, right? So a positive ion of hydrogen is a proton because it just has that positive proton in it because it lost its one electron that it has. And then, so we have to also account for the fact that there's an electron there. If you add the proton and an electron together, you get hydrogen. And so that means if you have a negative hydrogen, you have an extra electron. So that's why we have 2 electrons listed here as the components with 1 proton equals a negative hydrogen ion. So if you go back up here to NADH and FADH2, like FADH2, we're going to have 2 extra protons. But if we have 2 extra protons, we also need 2 extra electrons to come with the protons. So it's a full hydrogen because you see here we have 2 full hydrogens. And the NADH, we have a positive NAD. And so if we're going to add a proton to that, we need to have 1 electron that counters that proton and turns it into a full hydrogen. But we also need a second electron to counter that positive that is part of the NAD positive. So we need the 2 electrons to counter both of these positives. So when we add them all up together, we get a 0 charge NADH. Now these protons are pumped out into the inner membrane space. That's between the crista and the mitochondrial membrane that I was just showing you, or IMS. And then in the electron transport chain, it's going to remove all the electrons from these compounds. It's going to remove all the electrons, suck the electrons out, and then pass them down a row of complexes. They're just called complexes, like complex 1, complex 2, and you'll see what I'm talking about. I have it drawn out for us. And also you want to make sure you remember this in the electron transport chain because this is usually a test question in biology and microbiology. Oxygen is the final electron receptor, final electron receptor. So, and you'll see why, you'll see what the oxygen is doing and where it comes into play. It's just at the very, very end. It's not a big complicated deal, but this is usually a test question. So remember, oxygen is the final electron receptor. Okay, so here is a drawing, a diagram of inside the mitochondria. So here's the mitochondrial membrane up here. Mitochondrial membrane. So this is the outermost kind of a cell wall, if you will, of the mitochondria. And then inside the mitochondria, right inside that mitochondrial membrane, is the cristae, this loop-de-loop up and down uh, membrane that sits inside of the outer mitochondrial membrane. And inside, between the mitochondrial membrane and that cristae, this is what's called the intermembrane space. There, the intermembrane space. And inside of the cristae are some protons. These are these plus signs. These are going to be the same thing as writing down a hydrogen with a plus sign on it. It's the same thing. These are stand for protons, which is just a positive hydrogen ion. It's a hydrogen that's lost its electron. So there's a couple of them already in the mitochondrial center. But as you can see in the intermembrane space, there's many more than what's inside the center. There's many more outside of that center in the intermembrane space. And so the concentration of protons is higher outside of the center of the mitochondria and in the intermembrane space between the mitochondrial cristae and the mitochondrial, the outer membrane. There's a lot more. Now, the O's that we have in the center, the mitochondrial center, stand for oxygen. And there's some oxygens floating around in the center there, and they're going to get used at the next to last step as the final electron receptor. So that's a test question. Now, don't forget that what is the final electron receptor for metabolism? It's oxygen. Oxygen is the final electron receptor. Final electron receptor is the oxygen. And down on the bottom left of the screen, you'll see from the previous steps, we have our 10 NADHs, our 2 FAD2s, and the 4 extra ATP that we made from glycolysis and the transition step and the Krebs. Now, the first thing in the electron transport chain is this, see this first house? And I drew these little houses and cars and a tree, like you're driving down a road, okay? You're driving down a residential street, and so these are all your neighbors' houses and a tree, and there's some cars there, and we'll get to why I drew those different in a second. So let's start with number 1 here. This is called complex 1. And so when you see these Roman numerals, it's just complex and then whatever number the Roman numeral is. So this is complex 1. And complex 1 takes NADH and it turns it into, breaks it down into its components, NAD plus, NAD positive, and then it sucks up the electrons from that NADH, and it takes the extra hydrogens, the extra protons, and it spits it out the back door. So it spits it out the back door into the backyard. So this is where the protons go, the positive hydrogen ions, which I've also represented as just little pluses, so I don't have to write the H's the entire time, but it's the same, we're talking about the same thing. The pluses and the H pluses, they're the same thing, I'm just writing them 2 different ways. So the NADH is broken down by this complex 1, and the complex 1 sucks up the electrons, and it spits out the hydrogens in its backyard. Now, at the same time as that, this complex 2, the tree breaks down the FADH2s into its components. So it leaves the FADs behind, and it sucks up that electron. It sucks up those electrons. But this is a tree. This isn't a house. So you can't put the hydrogens out the back door into the backyard because it's a tree. It doesn't have a back door. So the tree, complex number 2, when it breaks down FAD, it actually leaves the hydrogens or the protons from the FAD inside the center of the mitochondria. It doesn't spit it out into the backyard. This tree one doesn't. So the NADHs go through complex number 1, which sucks up its electrons and spits out the hydrogens into its backyard. The FADH2s, the electrons are sucked up by this complex number 2, but it leaves behind both the FAD and the protons, the positive hydrogens. It leaves those 2 behind in the center of the mitochondria. Now, between this complex number 1 and complex number 2, you see this little car with a Q on it? That's coenzyme Q. So coenzyme Q I drew it as this little car because this enzyme, or this coenzyme is mobile. So it drives back and forth between the tree, complex number 2, and the house, complex number 1, and it picks up all of those electrons that are hanging out in both of those complexes. And then it drives past complex number 2, past the tree, and takes all those electrons and dumps them out in complex number 3. Okay, and people refer to this as it's playing hot potato because nobody wants to hold on to those electrons. So what's going on is these electrons are just getting passed down the road from house to house, from complex to complex, all along the road, all the way down the electron transport chain. So complex number 3 has those electrons that it got from coenzyme Q, from the mobile coenzyme, the car, and it takes the hydrogens, the protons that couldn't be spit out into the backyard previously from the FADH2. It takes those hydrogens and spits them out into its backyard. Complex number 3 does. Well, now we get to this another car with letter C on it, and this is called cytochrome C. That's cytochrome C. And cytochrome C is also another mobile coenzyme, just like the Q, the coenzyme Q back there, and it does exactly the same thing. It drives back to complex number 3, and it takes those electrons, and then it drives forward to complex number 4, and drops off the electrons at complex number 4's house. Now, after it drops off the electrons at complex number 4's house, complex number 4, not only does it do something with the electrons, complex number 4, you see all these protons here, just the protons that are inside the center. Some of these protons are going to get sucked up by complex number 4 and spit out the back door into the backyard. But some of these hydrogen ions, these positive hydrogen ions, or protons, as they call them, are going to stay put in the center of the mitochondria, because what this complex number 4 is going to do is it's going to, not only does it spit out some of the hydrogens out its back door into the backyard, but it spits back the electrons that have been being passed down the street here. It spits them back into the center of the mitochondria. So now we have some electrons, and we have oxygen, and we have a couple of protons, and these all bind together. So what does that give us? We have two H's, those two protons, two positive H's, and then we have one oxygen, and then we have two electrons. So those electrons bind with those positive H's, canceling each other out, giving us just regular H's, H2O. So that's water. So that makes water. So this is why oxygen is the final electron receptor in the electron transport chain, because from the electrons from complex 4 are spit back into the center, and they bind with the oxygen and some of the leftover protons that are hanging out there, and they make water. So now that that's all completed, we have one more step in the electron transport chain, and that's this funny looking doorknob down here to the right. And this actually turns, this doorknob turns, and we'll talk about that in a second. So as we've seen, we've gone through NADH getting broken down by complex 1. Complex 1 spits the hydrogens out, the protons out into its backyard, and it takes the electrons. Now, when it spits these protons out in its backyard, these protons will eventually travel around, all the way around until they mingle in with all these other protons that are in the intermembrane space outside of this little pump, this little doorknob looking thing. And the FADH2s are broken down into their components. FAD complex number 2 takes up the electrons, but complex number 3 takes up the hydrogens and spits them out into its backyard. So now those hydrogens in the intermembrane space go down, eventually travel down, and join the other hydrogen ions, the other protons, outside of this doorknob looking pump. And then complex number 4, which took any of the extra hydrogens, ions that we're not going to use, and sucked them up and spit them out into their backyard, those hydrogens eventually travel down and join the other protons in the space right outside the pump, in the intermembrane space. So now we have a whole bunch of these protons in the intermembrane space. So there's a high concentration of protons in the intermembrane space, and not really any hydrogens, or not really any protons inside in the center, inside the cristae in the mitochondria anymore. So since there's a high concentration of protons outside the cristae in the intermembrane space, and a very low concentration of hydrogen ions in the center inside of the cristae's folds, it is a very solid rule in the sciences that things will flow from their highest concentration to their lowest concentration. They always go where they're needed. Okay, so the hydrogens, since they have such a high concentration in the outside of the cristae and a low concentration on the inside of the cristae, they have a tendency to want to go back through the cristae into the center of the mitochondria, because things always flow where they're needed. So they're going to want to flow in the direction where there aren't a lot of them. It's a low concentration of protons. So the way they do that is they're not going to just diffuse through the cristae. They need to go through this pump, this doorknob looking pump thing. And so when the hydrogen ions, the protons, go into this pump, it makes the pump turn. It turns around in a circle. It just turns and turns and turns and turns, propelled by the force of these protons moving into the pump. It makes the pump turn. The pump takes that kinetic energy from it turning, and inside the pump, it has ADP and phosphate. And it takes these two substances, ADP and phosphate, and it smooshes them together to make ATP. And that's what is spit out back into the center of the mitochondria, is the ATP resulting from this kinetic energy forcing the phosphate to join the ADP and turn it into adenosine triphosphate, ATP, with 3 phosphates now, and it spits those ATPs back out into the center. And those ATPs are holding that energy, that kinetic energy from the pump turning, now is potential energy being stored in this ATP. So this is how you end up getting, for every 1 NADH, you make 3 ATP. For every 1 FADH2, you make 2 ATP. I always remember it because 2 and 2. So FADH2 makes 2 ATP, 1 NADH makes 3 ATP. So if we had, from the previous steps, 10 NADHs, and it makes 3, every 1 NADH makes 3 ATP, that means you're going to have 30 ATP from the NADHs. We had 2 FADH2s, and for every 1 FADH2, it makes 2 ATP. So if we have 2 of them, that's going to make 4 ATP. And then we have this leftover 4 ATP that we didn't do anything with it in this step. It was just already made from the previous steps. So 30 ATP plus 4 ATP plus 4 ATP equals 38 ATP, which is what is produced for the entire metabolism, aerobic metabolism cycle. Now, if we do fermentation instead, because if there's no oxygen and we have to go the fermentation route, that's a totally different set of numbers, it's a totally different amount of ATP. But if we're doing aerobic respiration with oxygen present, then this is the pathway that it follows, and this is how much ATP you're going to make per 1 molecule of glucose. And that's it. So please don't forget to like and subscribe. I can only tell if these videos are working and they're helping if I get likes and subscribers. So please don't forget to like and subscribe, and or just like. And if you have any questions though whatsoever, please feel free to leave a comment underneath this video, and I will get back to you as soon as possible. And there will be a free PDF download for this entire series of videos on the metabolism, on cellular respiration. All of these notes that I've drawn up here in this series of videos, this entire playlist is going to be in a PDF on my website at www.suzannestutoring.com.